Hello everyone. Welcome back to our lecture series of Gate in Data Science and Artificial Intelligence. This is lecture number 6 of Artificial Intelligence syllabus. So in the previous lecture, we have discussed about introduction to search problem, then what are different types of search strategies are there, uninformed search, informed search, adversarial search, and what are the different techniques used in each of the case, right? So this is lecture number 6. Here we are going to discuss about DFS versus BFS, that is depth first search versus breadth first search algorithm. Okay, so both are the part of uninformed search strategy. So both are the part of uninformed search strategies. We have discussed this both the algorithm in detail in the previous lecture. So please try to watch those video first. So up till now, whatever we have discussed, it's just the foundation of this particular AI course, or you can say introduction to a search problem, right? This video will give you overall idea about the uninformed search and what is DFS and BFS is. Okay. Now this is going to be a very important video, right? So please try to watch till end, and you can expect at least one question from this topic or this video itself. Okay. So we are going to discuss in detail. So let's start the session. Okay, so first, like exploration strategies, right? So whatever we have discussed in the previous session, just have put it in terms of wording here. So in DFS, what we do, DFS explores one branch of possibility as deeply as possible before backtracking, right? So in the case of artificial intelligence, what we can say, this can be useful when you want to exhaustively search a decision tree or state space. Right? For example, in game playing AI, DFS can be used to explore different moves and evaluate their outcome, right? So we have discussed one 15 puzzle example, if you remember in the previous lectures. So we have discussed this example and also maze example, right? For both the DFS and BFS, we have discussed these two examples. So please try to watch the previous videos. Now in the BFS, what happens? BFS explores all possibility at the current level before moving to the next level. So BFS goes level by level, right? So in AI, what we can say, this is valuable for finding the shortest path or optimal solution. So in the case of DFS, we may or we may not get the solution. And if we get the solution, that may not be an optimal solution. But in the case of DFS, it will give us the optimal solution, right? So for instance, in pathfinding algorithm for robotics or GPS navigation, BFS can be employed to find the shortest route. So please pay attention on this particular example, GPS navigation. So question can be asked based on this, like which of the uninformed algorithm is used in GPS navigation, right? So the answer will be BFS. So such type of questions you can expect based on the application also. So please try to note it down. Okay. So that's all about the exploration strategies in DFS and BFS. Okay. Now let us take one example, right? So this is basically a search space, right? So this is basically a search space. This is our root node, and we have number of branches. That is a child node, right? Now, in the case of DFS and BFS, what will happen? In the case of DFS, it will take one particular node. Say I am going from this node, root node to this particular node, right? Then it will try to go as deep as possible in that particular path. Okay. So DFS follows which principle? DFS follows last in, first out principle. So if we follow this particular last in, first out principle, if you see, we'll go like this, like from this node to this node, then we'll try to explore any of this node. Say, for example, this node, then we are going to explore this particular node, right? After that, we don't have any node to search, or this is our dead end. Then we'll backtrack to the previous unexplored node, and then we'll again explore this particular node, right? So like this way we'll follow. So this is my node 1, then this is my node 2, this is my node 3, this is my node 4, and this will be my node 5. So in the case of DFS, my fifth node will be this one. Right? But what happens in the case of BFS? So BFS follows which principle? That is first in, first out principle. Right? So if we follow this first in, first out principle, so what will happen in the case of BFS? So this is our first node. This is our initial state. Okay. So we are starting our search from this particular node. That is our initial state. So what will be my fifth node in this case? This will be a first and second will be my this node, right? But BFS go level by level, right? So my third node will be this, right? My fourth node will be this, and my fifth node in the search space will be this, right? So in the case of BFS, we go level by level. So my fifth node will be this particular node that is in level 2, but in the case of DFS, my fifth node will be this particular node in the case in the level 3, right? Okay, so I hope you understand this particular example. So this is based on whatever we have discussed in the previous lectures itself, right? So now this is what I have explained just right now, right? In the case of BFS, we start from here. This is node 1, this is node 2, node 3, node 4. This will be my node 5. And after the node 5, I will again backtrack and this will be my node 6, right? In the case of BFS, this will be my first node, second, third, fourth node, and this will be my fifth node, right? And this will be my sixth node. So this is level 0, this is level 1, right? And this is will be my level 2. So we are in level 2 while searching for 6 node, and in the case of DFS, we are in level 3 for my 6 node, right? So what DFS will do, DFS dives down the left part of a tree. Here you can see in this example. But in the case of BFS, what happens? It looks at all the nodes at one level before going to the next level, right? So that's how both DFS and BFS works. But now we want to compare both the search methods. So how we can compare, right? So there must be some criteria or component in order to compare this particular algorithms. So which are those components? Let us discuss that. So the search algorithm can be compared based on the following criteria, right? So the first criteria is completeness. So what is completeness here? That the algorithm will find a solution when there exists one, right? So if we say our algorithm DFS or BFS is giving me a solution, then we can say it is complete, right? If we are not getting a solution, then we can say it is incomplete. Now the next component is time complexity. So what is time complexity? So it basically how long does it takes to find a particular solution, right? That is what time complexity is. So we'll discuss this in detail. Now, what is space complexity? It basically how much space does the algorithm need, right? This in the previous lectures, but we'll also discuss in detail in this particular video. So that is space complexity means how much space, or you can say memory also, right? How much space or memory does the algorithm need, right? So the next is quality of solution. Quality of solution we can say like optimal solutions also, right? So suppose if some solutions are better than others, suppose we have multiple path to reach the particular goal state, but which one is shortest path, but which one is optimal path, right? So that will be a quality of solution. So quality of solutions means it is optimal solution, right? So these are the few criteria which are going to use to compare DFS versus BFS, right? Now let's talk about the completeness first. So there are two cases. The first one is when the search space is finite. So when we can say our search space is finite, so say for example, we have this kind of tree, right? We have just a tree here like this. And say suppose this is a level 2 till say suppose level 9, right? Now we have fixed number of level here, right? That is a finite state space in the particular tree, right? Then in that case, what will happen? So both DFS and BFS are complete for finite state space, right? So if we have finite state space, for example, we have just let us take one example. Just say for example, we have only level uh, 2 in this case. So both DFS and BFS will give us the solution because in the case of BFS, it will go level by level. So it will explore this one, this one, this one. Like this, like this, it will explore each and every node. So it will give us a required goal state. Same happens in the case of DFS. It will go as deeper as possible, then it will backtrack, but it will explore all the nodes, right? So both the DFS and BFS will explore all the nodes. So for a finite state space, we can say both will be a complete. It will give us the solution, right? So both are systematic and they will explore entire search space. That's what I discussed before reporting the failure. So suppose if we have finite state space and if they didn't found the required node or required node is not present, then it will report the failure, right? In the case of finite search space. So please make sure it is in the case of finite search space. This is because the termination criteria for both is what happens in the case of if our search space is infinite. So suppose in this case we are keep going like this, like this. We have infinite level of search space, right? And we have loop also in there like this. So what will happen in this case? So if state space is infinite, but a finite branching, then DFS may go down to infinite path and may not terminate, right? But in the case of BFS, what will happen? It will find a solution if there exists one, because it will go level by level, right? Not it will go as deep, then it will track to track, and then it will again explore. This happens in the case of DFS, right? But not in the case of BFS. So BFS will find a solution if there exists one, because it is going level by level, right? Right? So BFS will give us the solution. But if there is no solution, both the algorithm will not terminate for infinite spaces, because the termination criteria is they should explore all the nodes, right? But our search space is having infinite search spaces, and it don't have any required condition or goal state, so it will not give any solution, and it will never terminate, right? So that's what it says. So please try to keep a note of this particular points. It is very important. So that's about the completeness. So in short, what I can say, DFS and BFS both are complete, right? Both are complete in the case of finite search space. All right. But DFS will give us incomplete solution. So DFS we can say incomplete in the case of infinite search space, right? And BFS give us complete in the case of infinite search space. So please keep a note of it. It is very important, finite and infinite search space, because if you see any other resources on the internet, it will misguide you, because they will say DFS is incomplete and BFS is complete. That's not correct. It depends on finite search space or infinite search space. Okay. So please make sure you note this point. Okay. So that's all from this completeness. But before discussing about time complexity and space complexity, so let us discuss few other things. So in the case of computer science, the typical measure is the size of a state space graph. So in the case of computer science, if we want to measure the complexity of any particular tree like this, suppose this is our tree. So the complexity is measured by V plus E, that is V plus E, order of V plus E. So V is vertices, that is node in the case of graph, and E is the set of edges, that is links, right? So where V is the set of vertices, that is nodes of the graph, and E is set of edges, links. So this is appropriate when the graph is explicit data search, that is input to a search program. But this is not the case in AI, right? So in AI, the graph is often represented implicitly by the initial state, right? Actions, transition models, right? So what will be my initial state? What are the actions I can perform? What will be my transition state? And is frequently infinite. So based on such parameters, the complexity will be different in the case of AI, right? In the case of like theoretical computer science, we can say it is order of V plus E. It is both in the case of BFS and DFS, right? But in the case of AI, it depends on other factors also, right? So there are few factors which our complexities depend. So first one is branching factor. This is basically number of child nodes each node has, right? So if you consider this tree, so this node is having two child nodes. So this node is having two child nodes. This node is having two child nodes, right? So this is basically my binary tree. So my binary tree. So each node is having the two child nodes. So in this case, our branching factor is 2. And depth is basically depth of shallowest node from the root, right? So suppose this is my initial state, okay, and this is my final state, okay. This is my final state, or you can say goal state, right? I want to search this. So what will happen in the worst case of both the algorithm DFS and BFS? First, it will explore this and this. So at the last, it will explore this node. In the case of BFS also, first it explore this level, then this level, and this level also. And in this case, is the last level, right? So in the both the case, they have to search the same number of nodes, right? So we'll discuss this with the help of example, right? So if you understand this previous example, I can do like this, okay? So I can just draw, I can just consider like this, okay? This is my, so this will be my, you can see bounded representation of a such tree. So you can say like that. So here also we have considered this. Okay. Okay. Now let us assume that okay, this is our root node, and we are having the nodes at each level. Okay. So we have like this nodes like this, like this, like this at this level also, and here also like this. Okay. Till like this. Now looking at this particular graph, what we can say. Suppose our goal state is present on the extreme bottom side of the left hand, right? Here you can see. Then in that case, DFS will work fast because DFS will find this one fast while BFS will need to wait through exponentially growing layers. So BFS needs to go through layer by layer like this, like this, like this, like this. Then at the last, he will come at the his last step, last layer, and then he will find it out. But in the case of DFS, it will take one particular path and try to go more deeper. So in that case, DFS will find this particular node faster. But what if our goal state is present here? Okay, that is near to the root node and which is on the some right hand side or shallower node we can say, right? Then in that case, DFS will find this quickly, while DFS will take longer time as it shifts from left to right. So as BFS works level by level, so it will go like this, like this, like this, like this, and finally it will find it out by going at each level. But if you consider DFS, it will track one particular path. It will try to search till the dead end is reached, then it will again backtrack. Okay, so in this way, it will take more time for DFS to find this particular node, right? But in the case of BFS, it will find it quickly, right? So I hope you understand what I want to say from this particular graph. Okay, now let us discuss about the time complexity. So consider one tree here, like same binary tree will take. We have node 1, then we have two subchildren, then we have two child, right? So each node is having the two children here, right? So right, the root node of search tree is the start node, right? So this is our root node and this is our starting point. And suppose this is our goal. This is our goal state, right? We want to find this particular node. So at level 1, this is level 1, depth 1, there are B nodes, right? So B is basically a branching factor. It tells us number of child that a particular node has. So in this case, root node is having two child. So branching factor is 2. Now here also for this node it will have two children. For this node it will have two children, and here also it will have two children. So every node will have two children, right? Unless it is a leaf node. So that is what branching factor is. That is number of children that particular node can have, right? Now at depth 2, so this is depth 2. Here you can see B into B, that is 2 into 2, 4, right? And so on. So at a level D, say for example, let level D. So again, this is our level 3. So here you can see how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, right? It means 2 to the power 3. So what I can say in general, the number of nodes at a particular level is denoted by p to the power d. Right? So please remember this. The number of node at a particular level is given by b to the power d. So at level d, there are b to the power d nodes. Okay. Also given a tree of depth d, the number of internal node is I. So this b to the power d is number of node at a particular level. Now, what is number of internal nodes here? I. So this is given by like this. So I equals to b to the power d minus 1 divided by b minus 1, right? Where b is the constant branching factor. D is, assume that the goal occurs somewhere at the depth d only here. Okay. So suppose if you are using BFS or DFS, right? So both have to explore all the nodes before reaching to this particular node or this particular node. It's goal state, right? Or last level. So we can say at level D, there are b to the power d nodes and there are this number and this much of internal node. Okay. Now, if you observe one thing, say for example, let us take one example. Say we have branching factor of 2 only and say depth is 8. Okay. So D is 8 and B equals to 2. So how many nodes will be there at a depth 8 at the last level? It will be 2 to the power 8, right? But how many internal nodes will be there? So here I will be 2 to the power 8 minus 1 upon 2 to the power, sorry, 1 to the power minus 1. So here it will be 2 to the power 56 minus 1 and it will be to the power 56. So it will be to the power 55 and here it will be to the power 56. Right? And if you assume that, okay, a b equals to 3, then the difference between internal node and the node at a particular depth, at the last step, will increase. So what we can say that there are more number of leaf node. Okay, so there are more number of leaf node than number of internal node. So this is internal node, right? This is leaf node. Leaf node is basically doesn't have any children, right? Leaf node is basically don't have any children, don't have any child node, right? So if you observe, okay, in this particular tree only, there's 1, 2, 3, 4, 5, 6, 7 internal nodes are there, and 8 leaf nodes are there, right? So if you observe, if we are using BFS, that is breadth first search, it will go level by level. So till here, he has to explore only 7 nodes. But in the case of last level, he needs to explore 8 level, right? So here you can see as depth increases, the complexity will be more, right? Now let us try to discuss this in detail. So let us discuss about the DFS first, right? So we all know how DFS works. So if goal is on the extreme left, then DFS find it after examining D nodes, right? So that's what we have discussed in the previous slide. These are the ancestor of the goal node, okay? If the goal is on the extreme right, it has to examine the entire search tree. So if our goal is present on this particular and then DFS has to go through each node till he reach to this particular node. So on average, DFS will examine this v to the power d by 2 nodes. Okay, so please remember this. On average, DFS will examine b to the power d by 2 nodes. But what will happen in the case of BFS? So same example, we are keeping the depth same and branching factor same. The search arrives at level D after examining the entire subtree above it. So it will go level by level. If the goal is on the left, it will pick only one node, which is the goal node. If the goal is on the right, get it picks up in the end like DFS, that is it picks b to the power d nodes, right, at the level D. So even if it's BFS or DFS, if the node is present on the right hand of a extreme right end of a particular tree, then both will take the same amount of time because they have to explore same number of nodes, right? So on an average, the number of nodes that BFS has to go through is this much, and it's b to the power d, b plus 1, whereas b minus 1. Okay. Okay, so please remember this particular formulas. And if you compare, okay, so here in the case of DFS, it is b to the power d by 2. So if you want to compare this average number of nodes that each algorithm has to explore, then what we can do is do BFS divided by DFS, right? So it will be around b plus 1, b minus 1, right? Now if you observe, this ratio is always greater than 1, right? Because b plus 1, if you consider b equals to 2, so it will be 3. If you consider b equals to 3, it will be 4 by 2, it will be 2. So it is always greater than 1. So what we can say from this particular expression? So BFS needs to explore more nodes than the DFS, right? That's what it says. Now, suppose if we keep increasing the branching factor, say for example, let us take b equals to 3. So this ratio will become 4 by 2, that is 2. Now, if you increase b to 30, what will happen? B equals to 30, what will happen? That is 31 by 29, right? Suppose b equals to 100, what will happen? 101 by 99. So here you can see as we increase the branching factor, so ratio is getting minimum, right? So what we can conclude from this? So what we can conclude from this particular thing? with a large branching factor, both DFS and BFS tends to do same work, tends to do same amount of work, right? As we increases the branching factor, if the branching factor is large, then both will give the similar amount of, then both will take the similar amount of time, right? So this is what it says. So please try to remember this particular formula and this one also, okay, for comparison purpose. So I hope you understand what we have discussed till now. Now about the BFS part. So we all know how BFS works. So this is our tree, right? Okay, this is our tree. So BFS will go level by level, right? This like this it will go. So here it will explore one node. Here it will explore two node. Here it will explore four node, right? So in the case of B, what we can say, it will explore. So suppose branching factor is 2, then it is B. The branching factor is 2. At level at depth 2, it will be B to the power square, right? So if we go like this, at particular at depth D, it will be B to the power D, right? Then how many nodes? So in the worst case, if this is our depth D, right, and this is our goal state, right? Goal state is present. In the worst case, BFS needs to explore each and every node, right? And in that case, it will be 1 plus B square plus B cube plus till B to the power D. So this much amount of node that BFS has to explore, right? So it is basically order of B to the power D. So what we can say, the time complexity. So this is very important thing. Time complexity for BFS is basically a order of B to the power D in the worst case. Now same I can say, if our node is present on this particular extreme right end, then it has to explore all the nodes, right? Then in that case, what I can say, for space complexity. So our space complexity is also order of B to the power D. Okay, so in the case of VFS, both time and space complexity is order of B to the power D. So please remember this, it is very important point. Okay, now if we say, if we assume B equals to 10, so if we assume branching factor equals to 10, suppose this node is having 10 children, right? This basically the root node is having 10 children like this. And this node is also having 10 children. This node is also having 10 children, right? So in this case, like each node is having 10 children, then at particular depth 2, it will be around 110 nodes, right? At particular depth 4, it will be around 11,110 nodes, right? So here you can see the time and the memory requirement for BFS, right? The number shown is assuming for the branching factor B equals to 10. So here you can see the memory requirement are bigger problem for breadth first search than is the execution time. Because one might have to wait for 13 days for a solution to an important problem with a search depth of 12, right? For a search depth of 12, it will take 13 days. And how much memory it will take? It will take around 1 petabyte memory, right? So we are considering worst case, okay? Worst case scenario, the worst case scenario, right? But no personal computer has the petabyte of memory it would take, right? So in order to process this much amount of data, 1 petabyte data, right? So we require supercomputer only, right? But fortunately, other strategies require the less memory. So yeah, so if our search space is bigger, then BFS will not work in that case. If your problem has solution at depth 16, so here you can see, as we increasing the depth with a constant branching factor of 10, then according to the assumption, it will take around 350 years for BFS to search it, right? So it is not possible to have such a system which will process 10 exabyte of data. So yeah. So here you can see the limitation of BFS. As we keep increasing the depth, so if our search problem is having a longer depth and having the branching factor of say 10, then it is not possible for BFS to do that, right? So in general, what we can say, exponential complexity search problems. So this comes under exponential complexity search problems cannot be solved by uniform method for any but smallest instance. Right? And same will work in the case of DFS also. So that's what we have studied today. So time complexity in the worst case, BFS also has a time complexity of order to the b to the power d. However, BFS systematically explore all nodes at each depth level before moving to a next level. It is particularly efficient in finding the shortest path in an unweighted graph because it guarantees that shallowest node is reached first because it will go level by level. Then what is space complexity in BFS? The space complexity of BFS is typically order of b to the power d. Yes, that's what we have seen because it stores all nodes at each depth level in a queue. BFS can consume significant amount of memory, yes, especially when branching factor is high or the tree is deeper. It guarantees that it explores the shallow nodes first, but this comes at the cost of increased memory storage, right? Now for DFS, in the worst case, DFS can have time complexity of same order of b to the power d. If the search tree is deep and has a large branching factor, DFS can take long time to find a solution because the time complexity for both BFS and DFS is same, that is order of b to the power d. DFS can perform relatively well when the solution is shallow or located early in the search space, that is for small d, right? Now, what is space complexity for DFS? The space complexity of DFS is typically order of b into d, which accounts the maximum depth of the search tree. And so it uses memory proportional to the depth of the tree because it needs to store all nodes along the current branches in the strand. So DFS can be memory efficient. So important point, DFS can be memory efficient when depth is limited, but it may run into memory issue with the deep search trees. So DFS is also has its own limitation, but the time complexity is order of b to the power d, and here order of b into d. Okay, so please note it down. Okay, now this BFS also DFS. So with respect to time complexity component, then DFS may be faster in some cases, especially if the goal state is found relatively quick. However, in worst case scenario, it can take longer than BFS as it might explore deeper branches first, right? BFS ensures the shortest path in unweighted graph, making it ideal for scenario where finding the optimal solution quickly is crucial. And what is space complexity? In terms of space complexity, DFS often requires less memory compared to BFS. So important point. It can be asked in exam. Now, in the case of AI, this can be advantages when dealing with limited memory resources or deep search history. DFS typically consumes more memory as it needs to store all nodes at the current level, and this can be concerned when memory is constrained. Right. So all this thing we have discussed with the help of example. Now, what is quality of solution? So up till now, we have discussed completeness, time complexity, and space complexity. Now, what is quality of solution? Right. Basically, optimal solution, right? So in the case of DFS, there is no guarantee that we will get the optimal solution, but in the case of BFS, we can get the optimal solution, right? So we can get the optimal solution. So that's it from this particular slide. Okay, so please remember in the case of DFS, there is no guarantee of getting optimal solution, but in the case of DFS, optimal solutions we can get, right? So that's it. Now let's summarize the point, whatever we have discussed. So BFS is effective when search tree has low branching factor. BFS can work even in trees that are infinitely deep, right? BFS requires a lot of memory as number of nodes in level of the tree increases exponentially. BFS is superior when goal exists in the upper right portion of a search tree. BFS gives optimal solution. That's what we have discussed. Now in the case of DFS, DFS is effective when there are few subtrees in search tree that only one connection points to the rest of the state. DFS is best when goal exists in the lower left portion of the search tree, right? DFS can be dangerous when the path closer to the start and further from the goal has been chosen. Yes. So DFS is memory efficient as the path from start to current node is stored. Each node should contain state and its parents. and DFS may not give optimal solution. That's what we have discussed. So we have summarized all the 4 points what we have discussed in this particular lecture, right? Now, what are the applications? So DFS is commonly used in AI for tasks that involve deep exploration, such as search algorithm in game playing, right? And certain types of decision trees also, like Minimax for a game AI. But BFS is applied when you need systematically explore all possibilities at the current level, particularly in cases where the shortest path or optimal solution is essential. For example, it's used in pathfinding algorithm, natural language processing. So pathfinding algorithm is basically our GPS, right? So if anyone asks you which algorithm is used in GPS navigation, so BFS is the answer, right? Now, what's the conclusion? So in artificial intelligence, the choice between DFS and BFS depends on the specific problem, the nature of the search space, and the trade-off between depth, breadth, first search exploration. So yes, it depends on the case to case and specific problem we have, right? Now both algorithms have strength and weaknesses, and selection should be based on the problem's requirement and constraint, right? So that's it from this particular lecture. I hope you understand whatever we have discussed it today. So if you have any question, you can ask in the comment section. Okay. So please take a notes of it. It is very important video. Okay, you can expect at least one question from this. Okay, so 99.99% you can expect one question from this particular video itself. Okay, but in order to understand, you should watch the previous lectures also. Okay, so that's it from my side. So we have discussed BFS and DFS. Next we'll discuss about uniform cost search and depth limited DFS. Okay, depth limited or depth bounded DFS we'll discuss. Okay, so there are other components of this algorithm also, like by using pseudocode also we can understand this, but I am not touching that part. We don't know what is the level of the question of GATE exam. So first we'll try to cover all the syllabus. So first we'll cover all the syllabus. Okay, then at the end we'll try to again we'll come back to our syllabus and we'll try to understand the concept by using pseudocode. Okay, so pseudocode, so it will help you to understand the how algorithm works, right? So currently we are just focusing on the conceptual part. Okay, so that's it from my side. Thank you.